Hello, welcome back. In this video, we are going to learn about interdomain routing protocols. The agenda is we will introduce you to interdomain routing. After that, we will understand the generalized path vector routing that is normally used for interdomain routing. And one example of path vector routing, that is a border gateway protocol, will be discussed next. Introduction to interdomain routing. Let us understand the concept of interdomain routing. Let's say we have two autonomous systems, AS1 and AS2. Here we have several routers and the nodes of the network which are connected to one another. And here also we have routers and other nodes of the network which are connected to one another. Now, if packets are transmitted from one node to the other node within a single autonomous system, or we call it a domain, then it is known as intradomain routing. And if the packets need to be transferred between the domains, that is from here to here, then we call it interdomain routing. Now, in previous videos, we have learned about intradomain routing, where we have learned about distance vector routing and link state routing. Both of these are interdomain routing and they cannot be used for interdomain routing because of scalability issues. Distance vector routing, if you recall, suffers from instability. Instability occurs if there are more than fewer hops in the domain. Similarly, link state routing requires large resources for creating the routing tables if the domain is very much larger. So there is a need of a third routing protocol that is normally used for interdomain routing, and that is the path vector routing. This path vector routing is similar to distance vector routing in the sense that the entire path is defined by the speaker node. We will shortly know what a speaker node is for an autonomous system, with the only exception that the metric is not defined. So initialization is again the first step as in distance vector routing. Here there is a concept of a speaker node. The speaker node is actually the main node of an autonomous system which can communicate with all other nodes of the network and basically forwards information to the speaker node of other autonomous systems. Then after initialization, sharing of information is done as in distance vector routing to update the routing tables. Then updating is done for each of the routing tables. There is a term which is called loop prevention. This loop prevention is done to prevent the instability. The router should discard the message if it finds that its autonomous systems is in the path list to destination. So this would definitely prevent the loop as it is caused in the distance vector routing, which basically causes the instability. Then policy routing is again another term which is used for path vector routing. Here the router should check the path in the received message, and if it finds that its autonomous system is listed there, then and it is against the policy, then it may ignore that path and the destination, and later on it may not share the information to other autonomous systems. Optimum path is based on the smaller number of ASes, that is the autonomous systems, and also it should take care of the security features, of the safety features, and the reliability features. In distance vector routing, for the routing information protocol, we have seen that it depends on the number of hops, and in OSPF, which depends on the minimum delay, which is based on the link state routing. So metric here is not defined, but rather it defines the number of autonomous systems that must be covered in the routing table. So let us first look at the initialization, that is initial routing tables. So let's say we have the autonomous system 1, where there are 5 nodes, A1, A2, A3, A4 and A5. We have this second autonomous system AS2, where there are 4 nodes, B1, B2, B3 and B4. We have the third autonomous system AS3, where there are 3 nodes, C1, C2 and C3. We have the fourth autonomous system, where there are 4 different nodes, D1, D2, D3 and D4. Now, this is the path through which any node of this autonomous systems can connect to other nodes of the next autonomous system. These blue lines indicate the path. So in order to go from this autonomous system to a node of this autonomous system, it has to follow this path. To go from AS1 to AS2, it has to follow this path. From AS2 to AS3, it has to follow this path. And from AS3 to AS4, it has to follow this path. So what is the initial routing table for A1? So the routing table consists of the destination and the path. Here no metric, that is cost or hop count, is given, as we have seen for the intradomain routing. So what are the destinations? Possible destinations for A1 can be A1, A2, A3, A4 and A5. Because it has no information of other autonomous systems unless and until it gets the sharing information and updates the routing table. So initially it knows only its immediate neighbors of its own autonomous system, and it gives the path, so it can go via this path, so autonomous system 1. For the B1 table, again the same thing happens. There are 4 different nodes and it can go via this AS2. For C1, it can go via AS3 and there are 3 nodes. For D1, it is an autonomous system AS4, so there are 4 different nodes and the path will be AS4. Next is updating the routing tables. Once the autonomous systems get their information from all other neighboring autonomous systems, the routing tables must be updated. So let us look at the updated routing table of A1, B1, C1 and D1 as example. So here we can see that A1 can go from A1 to A5, or B1 to B4, or C1 to C3 and D1 to D4. Similarly for B1, C1 and D1. So what should be the path? In order to go to A1, it has to take the autonomous system AS1 and till A5. Now in order to go to B1 to B4, it has to take the path AS1 and then AS2. In order to go to C3 and C1 and C2, it has to take the path AS1 and AS3. And for D1 to D4, it has to take 3 paths. So AS1, AS3 and AS4. Similarly, we can fill up the routing tables of B1, C1 and D1. Now, let us turn our attention to one of the protocols which is based on path vector routing, and this is called the BGP or Border Gateway Protocol. This Border Gateway Protocol has 3 types of autonomous systems. One is the stub autonomous system, second one is the multi-homed autonomous system, and the third one is a transit autonomous system. A stub autonomous system is one which is connected to only one autonomous system. A multi-homed autonomous system is an autonomous system which can be connected to many other autonomous systems like AS2, AS3 and AS4. So it can act either as a sink, or a source. So it can receive information from all other autonomous systems and can send information to these autonomous systems, unlike stub autonomous system where it can only send and receive from a single autonomous system, which is its neighbor. A transit autonomous system is a multi-homed autonomous system which supports the transit message transfer. What is the meaning of transit message transfer? Let's say AS3, AS2 and AS1. A multi-homed autonomous system does not support transit information. What is the meaning of transit information? Transit information means, let's say there is autonomous system AS4 which wants to send message to autonomous system AS3. It cannot use autonomous system AS1 as an intermediate autonomous system to send the message via AS1. But transit autonomous system can support transit information to be transferred. So this is the difference between multi-homed autonomous system and transit autonomous system. Let's understand path attributes. There are two types of path attributes. One is the well-known path attributes and the other one is the optional path attributes. Let's first understand what a well-known path attribute is all about. A well-known path attribute should be recognizable by every router. Now, this well-known path attributes can be of two types. One is a mandatory attribute and the other one is a discretionary attribute. The mandatory attribute is one which must appear in the description of the route, whereas discretionary attribute may or may not be included in the update message. And these two form a part of well-known attributes which the router must recognize. The optional path attributes may not be recognizable by the router. Now, optional can be of two types. One is transitive and the other one is non-transitive. The transitive optional path attribute must be passed to the next router that has not implemented this attribute. Whereas for non-transitive, it must be discarded by the next router that has not implemented this attribute. Now, BGP can have two different types of sessions. Sessions means the communication paths. One is the external one and the other one is the internal one. The external BGP sessions means communication path that takes place between two routers in two different autonomous systems. And internal BGP sessions means the communication path that takes place between two routers or nodes within a single autonomous system. So let us understand the sessions with the help of this diagram. We have here two autonomous systems, AS1 and AS2. AS1 has nodes A1, A2, A3, A4 and A5, and AS2 has nodes B1, B2 and B3 and B4. Now, when there is a communication between A1 and A2 or A2 and A3, this is known as the IBGP sessions or internal BGP sessions. Whereas, if you want to communicate between A1 and B1, then it is the eBGP session or external BGP session. To summarize, in this video, we have learned about the concept of interdomain routing. We have understood what is the scalability issues and node instability issues that we found in interdomain routing protocols like OSPF and RIP. And we introduced the readers to path vector routing, which is an interdomain routing protocol, which is basically based on distance vector routing. But unlike distance vector routing, it does not send the metric, whereas it sends only the autonomous systems or the path. And BGP, we have touched upon BGP. This is Border Gateway Protocol, and this is an example of path vector routing. Thank you.